I'm Jonathan Wainsberg, Associate Professor of Philosophy at the University of Toronto. Today I'll tell you about Bertrand's paradox, what it is and why it's so important. By the way, the name Bertrand's paradox comes from a 19th century mathematician, Joseph Bertrand. He published a famous example of it in 1889, but his example's a bit tricky. So we'll use an easier one from the philosopher Bas van Fraassen. Here's the example. Imagine a factory that cuts squares of wood. The edges of the squares are always between 1 foot long and 3 feet long. Now ask yourself, how likely is it that the edges of the next square they cut will be between 1 foot long and 2 feet long? Well, 1/2 is the obvious answer. The range of possible lengths for the edges is 1 to 3 feet. Imagine a number line from 1 to 3. The 1 to 2 range is half of that, so half of the possible lengths are between 1 and 2 feet. So far so good. But now here's the turn. We're going to ask the same question in different words, and we're going to get a different answer. How is that possible? Let's see. Consider this question. How likely is it that the area of the next square will be between 1 square foot and 4 square feet? We're switching from talking about the lengths of the square's edges to talking about its area. But this is actually the same question as before. Remember, we're talking about squares here, and for a square, having edges between 1 and 2 feet long is the same as having an area between 1 and 4 square feet. The area is just the square of the length of the edges, and 1 squared is 1, and 2 squared is 4. So the 1 to 2 range for length corresponds perfectly to the 1 to 4 range for area. So, what's the probability that the area will be between 1 and 4 square feet? It's 3/8, or so I claim. How did I get that answer? Well, the area of these squares is always between 1 foot and 9 feet. The edges are always between 1 foot long and 3 feet long. 1 squared is 1, that's the bottom end of the range, and 3 squared is 9, that's the top end. So let's picture another number line, this time from 1 to 9. What portion of that line is the 1 to 4 range? 3/8. So the probability is 3 out of 8, or about 38%. Uh-oh, we got two different answers to the same question. When we did the calculation in terms of the lengths of the edges, we got 1/2. When we did it in terms of the area, we got 3/8. So which answer is right? At this point, you might be thinking we screwed up the arithmetic somewhere in there. But the arithmetic is fine. Go back and check as many times as you want. You won't find any errors in the calculations. So what's going on here? Well, it's a well-known mathematical fact that the size of a range of possibilities depends on how you describe it. In terms of the lengths of the edges, the 1 to 2 range is half the total range from 1 to 3. But in terms of area, it's smaller. When we switch to area, we square all the numbers, and squaring larger numbers increases them more than squaring smaller numbers does. So the range from 1 to 2 grows, but the range from 2 to 3 grows by even more. So the first range of possibilities looks smaller from the perspective of area, even though it looks the same size from the perspective of length. So Bertrand's paradox isn't the result of any calculation error. It's the result of using the size of a range to determine its probability. Put another way, the paradox arises from a famous principle known as the principle of indifference. In its simplest form, the principle of indifference just counts possibilities. Imagine you're at a racetrack and 3 horses are running, A, B, and C. What's the probability that horse A will win? Well, 1 out of 3, obviously. Let's assume ties are impossible just to keep things simple. In general, the principle of indifference says, when the number of possibilities is n, each possibility has probability 1 out of n. For the flip of a coin, there are 2 outcomes, heads and tails, and each has probability 1/2, 1 out of 2. If there's a dartboard with 4 sectors, each has probability 1 out of 4 of being where the dart lands, and so on. Notice, by the way, that the principle of indifference only applies when all you know is what the possible outcomes are. If you have more information than that, for example, if you know that horse A is sick, that changes things. Then the sick horse is less likely to win than the other 2. The principle of indifference doesn't apply then. It just tells you what probabilities to start with before you get any relevant information. Okay, so how about when there's a continuum of possible outcomes? In our square factory example, the length of a square's edges could be anywhere between 1 and 3 feet, and you can't count all the points in that range. Well, then the principle of indifference says to use the size of each range to determine its probability. If a range of possibilities takes up half of the total range, then it has probability 1/2. If it takes up 1/3 of the total range, then it has probability 1/3, and so on. And that's how we end up with a paradox. Because we saw that the size of a range of possibilities depends on how you describe it. Using length, we get one answer, 1/2 in the square factory example. Using area, we get a different answer, 3/8 in that example. You might be surprised to learn that Bertrand's paradox turns out to be a big problem for scientific reasoning, because the principle of indifference is supposed to answer a crucial question. It tells us where to start when we're working with probabilities. And probabilities lie at the heart of pretty much every branch of science. Whether it's medicine, psychology, or physics, every field of science relies on statistical reasoning. And the same goes for our daily decisions, from dietary choices to political policies. In fact, those decisions often rely on the findings of scientific research. So the principle of indifference is supposed to determine the starting point for all scientific inquiry. But we've seen that it leads to contradictory results. In fact, this problem has had a huge impact on the development of modern science. For over a century, statisticians have struggled to find methods that work around it. But they still disagree and argue about how to deal with it. And as a result, they even disagree about what to make of the results of various scientific studies. So Bertrand's paradox goes right to the heart of debates about science and its objectivity. Bertrand's paradox is closely connected with another famous philosophical puzzle, the Puzzle of GRU. Bertrand's paradox shows how the probabilities we get from the principle of indifference depend on whether we choose the language of length or the language of area. The Puzzle of GRU shows how to pull a similar trick on another famous principle underlying scientific reasoning, what David Hume called the principle of the uniformity of nature. So both puzzles show how core scientific principles seem to depend on the language we choose. Well, that's it for Bertrand's paradox. Thanks for watching. To subscribe to Wireless Philosophy on YouTube, click here.